All right, so here's the agenda for the day. In the next 40 minutes, you'll hear about what artificial intelligence is and what it is not. We'll examine the differences between artificial intelligence, machine learning, and deep learning, and how the three can be used in cybersecurity. We'll then talk about supervised and unsupervised learning and the pros and cons of using each. We'll then step into a practical world and look at examples of time count and pattern anomalies of entities in the network. Risk scoring is another major thing that you'll hear about today. What is it and how can peer grouping used to calculate risk? It is also important for security analysts to build a timeline or a sequence of anomalies that led to an incident. So we'll be discussing that next. And then we'll be talking about incident management with anomalies and end it all with a real life example of a cyber attack. So that's what we'll be doing in the next 40 minutes. And that's why you need to stay with me until then. By the way, during the course of this webinar, if you have any questions, please use the Q&A option on your webinar panel. We'll have some time set aside for Q&A at the very end. So before we get started with things and discussing the topic itself, I would like you to imagine a situation with me. Imagine a scenario where a biotechnology company is working on some breakthrough research to find a vaccine for a completely new type of virus. Let's also imagine that two employees of this company are bribed by a competing biotechnology company to steal the data about all the research and hand it over to them. So over time, the two employees start stealing the data. And since these two employees are trusted within the company, no suspicion is ever raised. This results in the company losing out on its business and market share. Now, this is a very, very grave situation, and it should have never happened. Data is the most important asset, and it should never be stolen from any company. In recent years, we have seen quite a lot of insider attacks take place, similar to the example we just went over. Likewise, we also have external attackers making use of sophisticated methods to take down organizations. In such a climate, organizations should have the right defenses and controls in place to track all anomalous activities. Because think about it, working with just rules-based detection systems that track activities that a security analyst is particularly looking for, well, no doubt about it, it gives one level of defense. But in addition to that, companies need a mechanism to track anomalies in the network. Now, in our own example with a biotechnology company, there was no way that a purely rules-based system could have detected that the two employees were stealing data from their own employer. So how do you track anomalies in the network? Well, you've got to use artificial intelligence and machine learning to do that. So first up, let's talk about artificial intelligence, machine learning, and deep learning. Now, many times, these three terms are used interchangeably, but this is actually not accurate. There is a very clear difference between the three, and cybersecurity analysts need to understand this difference so that they can use the right technology at the right place and also know what technique is being used for detection. Now, when it comes to artificial intelligence, it's a very, very general term that denotes any activity by a computer that mimics human behavior. It is all about using technology to make a machine think, learn, adapt, and reason just like a human. Now, machine learning, on the other hand, is a way, if you will, to implement artificial intelligence for practical purposes. It is all about creating a software that has the ability to learn. To put it a little differently, it's not about creating a software that works based on rules that are explicitly programmed, but software that is adaptive, learns, and becomes better with experience. Now, it goes without saying that multiple things can be done within the software algorithms in the way that it is programmed to make it a more accurate machine learning model. So there are many, many machine learning models that can be implemented within the software. And then finally, you've got deep learning. This is a subset of machine learning. Let me explain what I mean by that. This is a specific form of machine learning. So here we are talking about artificial neural networks that imitate a human brain. In traditional machine learning, the human or some human being is still programming the machine to make it learn with experience. So the learning, well, it's very, very linear. Whereas in deep learning, the machine learns without human intervention. It can analyze really huge amounts of data that is unstructured and unlabeled, and it uses its neural network to gain that context. So in my talk today, I'll be mainly talking about how machine learning can be used in cybersecurity. So we'll be focusing on this part right here. Next week, when we take a more futuristic approach and talk about how cybersecurity is going to evolve in the years to come, we'll talk about deep learning and artificial intelligence. But that's 1 week from today. So machine learning in cybersecurity. Well, it turns out that there are 3 main techniques when implementing machine learning for security. And these are what you see on your screen right now. So you have supervised learning, then there's unsupervised learning, and finally you've got semi-supervised learning. In supervised learning, a human basically feeds both the input and the output to the machine. Now, the principle is that you keep doing it enough times and the machine is going to be able to learn a pattern. So the input would be samples that are fed into the learning model, and the output would be the classifiers or the labels. Let's take a very, very simple example. Let's say that you have a really long list of executable files or network data. So that's what you have here. You have a lot of network data here, and these would be your samples. And then you could label these samples as 0 or 1. So, this particular network data, you're labeling it as 0, and then you have something else, you're labeling it as 1. So you could label it as 0 or 1. So that would stand for malware in case it's 0, and it's a safe file or safe network data in case it's 1. Now, over time, the system is going to learn the patterns of files that are malware and the patterns of files that are safe. It can then make a prediction about a new file that has to be analyzed. Basically, what we are trying to do is we are creating a fully labeled data set and then finding some function that relates the input and the output. So this flowchart at the bottom of your screen explains it pretty well. So you have the data that you need to divide into your training data, and you've got your test data as well. So you divide it into 2 parts. Usually, the training data is going to be a lot more. We go with a ratio of 70% to 30%, as an example. And then using the training data in supervised machine learning, we'll be creating a training model that will help us make a prediction. Then on the test data, we apply the training model to make a prediction about the test data. And then basically in the evaluation stage, we are just checking if the prediction is actually true, because we have the test data, right? We know what the result or what the output has got to be for the test data. We apply the training model and then we see if what the predicted value and the test on the value that we know to be true, if they are equal or not. And in case they are not equal, we can always go back, use a feedback mechanism within this model to make the system learn better. So we can improve the machine learning model. So that's how this works. Now, in a security incident, the system is going to make a prediction about an entity's behavior. And then ideally, it's got to check with a security analyst whether it's really an anomaly. The analyst is going to provide the feedback. The system learns more, and it will use this learning for the next time. So basically what we have done now is we have just described how supervised machine learning works. In unsupervised machine learning, there are only inputs. So you've got the data, but you've got no output. So how does this really work? Well, it's up to the system to discover patterns in the data. Once the patterns are discovered, they can then be shown to the security analyst so that corrective action may be taken. In unsupervised learning, at the very beginning, there are no right or wrong answers. The system is only trying to look at the data and make sense of what it says. Now, one of the main ways to implement unsupervised learning is through the use of clustering algorithms. So that's what I've got on the screen right here. Now, you've got a large amount of data, let's say, and you're just going to plot it in a graph. This is called a vector space model, and you've got all the data laid out over there. And the system tries to create clusters or groups of entities that exhibit similar behavior. So in this image here, what is being done is we are arranging all the data and we are trying to find these clusters here. So we've got 3 different clusters, and we can say that with certain authority that all of these data points, they fall into one cluster because they exhibit very, very similar behavior. Likewise with cluster 2 and likewise with cluster 3 as well. And then take a look at this. This flow diagram explains how unsupervised machine learning actually works. Data comes in, it's transformed into cluster data. And then, of course, we do something similar to what we did with supervised machine learning. We've got to evaluate our prediction. In cybersecurity, users who log on to a network between specific time ranges can be a part of a cluster. So let's say users that log on to the system between 7 and 8 a.m. in the morning, they are part of cluster 1. So that's how cluster 1 gets described. Users who access certain servers can be part of yet another cluster. So that's cluster 2. So probably some finance data is stored in a particular server, and all the users who log on to that particular server and access that data, they can be part of cluster 2. And servers that are accessed at certain times can be part of yet another cluster. So let's say that there is some payroll data that is housed in a particular server, and that server is only accessed at certain times of the day by certain users. So those users will be part of yet another cluster. So that's how clustering actually works. The system is trying to put different users based on their behavior into a particular cluster. So basically, this is how, this is the algorithm that unsupervised machine learning follows. And then finally, you've got semi-supervised machine learning, or it's also called reinforced learning, where some of the data is labeled and some of the data is not labeled. And in my personal opinion, this is the way to go. This gives security analysts the option to teach the system about threats that are unique to their network and their business environment. And at the same time, it uses both supervised and unsupervised learning, because some of the data is labeled and some of it is not. So, it can be used in a combination. So this is going to help us reduce a lot of the false positives when it's applied in a cybersecurity kind of a use case. So with semi-supervised learning, or basically using a mix of supervised and unsupervised learning, a security analyst can analyze the raw data, glean information, acquire knowledge, build insight, and finally gain wisdom. And this really should be our goal, this part here of gaining the wisdom. By the way, in case you're wondering, in case you're interested, this is called the DIKIW model. So this is what every cybersecurity analyst wants to do. Transform that data into wisdom. But whatever algorithm is being used, the organization must make sure that all the data gets collected from across the network. It is necessary to collect data from network devices such as routers, switches, firewalls. You should collect data from network file shares, databases, applications. You should be able to collect data from Active Directory, your cloud infrastructures, privileged access management systems. And apart from all of that, you also need to collect data from your threat sources, right? Your data loss prevention systems. You've got to be able to get data from your vulnerability scanners. So pretty much anything in the network, you should be able to bring in, and you should be able to analyze using machine learning algorithms. Now let's talk about how the analysis and contextualization can actually take place and how anomalies can be detected. As you can see on this slide, there are 3 primary types of anomalies that your machine learning system has to detect. These are time anomalies, count anomalies, and pattern anomalies. To find out what's anomalous, we first need to calculate a baseline of expected activity for every user and entity in the network. Because think about it, to know what's not normal behavior, we first have to understand what normal behavior actually is. So that's the first step. So we have to calculate a baseline for every user and entity in the network. With time anomalies, we are asking questions such as, did a user log on at a time that fell out of their expected range? For example, take a look at this. We have a user here called Steve, who's expected to log on between 2 and 2:15 p.m. But what is actually happening is this right here. They're showing a log on at 1 a.m. So is this a case of some kind of malicious activity? So as a security analyst, we've got to be able to double check on this. We've got to be able to see and get to the bottom of what Steve is actually up to. So that's what a count anomaly is. What is expected and is our observed value, is our obtained value going out of that expected range. So we can track this as a time anomaly. Next up, we have count anomalies. And with count anomalies, we are asking questions such as, are software and services being installed on hosts way too many times during a given time period? So let's take an example of a count anomaly. Take a look at this. So we see that there is this particular software from this vendor being installed on this host. So here's the IP address of the host by this user called Martin. And how many times it is being installed? It's being installed 250 times. You heard that right. Can you believe it? 250 times. I mean, it's never possible, right? So there's, I mean, without even looking at the threshold, we know that something strange is happening. But anyways, take a look at the threshold. What's expected is 7 such activities. And that is why this is an anomaly. This is a count anomaly. So is this a case of an insider attack? Is Martin doing something malicious? Next up, we have the third type of anomaly. That's the pattern anomaly. And as the name suggests, we are looking for unusual patterns of events. So also here, we are not looking at hosts, users, and time in isolation. That's what we did with time and count anomalies, right? With time anomalies, we're looking at time specifically. With count anomalies, we were looking at counts specifically in a particular time range. So that's what we were doing. And we were also looking at time anomalies and count anomalies for specific users or entities. So with time anomaly, we saw that, Steve was doing something strange. And then when it came to count anomalies, we saw that Martin was doing something strange. Now in pattern, like I said, we are going to be looking at patterns of events. So let's take an example here and you'll immediately see how this is different. Take a look at this. So here we have got this software from this vendor being installed on this host by Martin. Now take a look at this. The pattern that is being analyzed is this: host name, username, and time. Now it just turns out that the host name and username part of the pattern seems to be absolutely fine. However, there is a deviation when it comes to the time of the activity. So that needs to be detected as an anomaly. Take a look at this. What is expected in this particular pattern? So when it is Martin working on this particular host with this IP address, what is expected is activity between 7 to 8 a.m. or 5 to 6 a.m. That is completely expected. But an activity is happening at this particular time. It's happening at 7:07 p.m. And this is the obtained value between 7 and 8 p.m. and that is being tracked as an anomaly. Again, we are not looking at time in isolation, but we are putting 3 different variables together to say that this is a pattern anomaly. So how does the security analyst use this in a practical sense? From here, the security analyst should be able to pivot and see exactly why any of these were anomalies. What was the underlying data that led to this anomaly detection? Security analysts should not have to just rely on an analytics black box and be in the dark about what goes on in the back end. They should be able to clearly see how far the observed values are from the expected values so that they can understand the risk level and the gravity of the situation. This is called anomaly visualization. For example, let's say that, what is expected is, an activity between 7 and 8 a.m. And what has actually happened is an activity between 7 and 8 p.m., right? Let's say that the activity actually happened at 9 a.m., which still falls out of what is expected. It still falls out of the expected range, but it is not as much a deviation, right, from what is expected, because the deviation is less. So in that case, the risk should also be less, and the security analyst should be able to deep dive and look at that data, should be able to visualize that, that particular anomaly and take the right kind of action. So all of that is very much necessary when you're working with these, anomalies. And then comes peer grouping. This is very critical when using machine learning to detect anomalies in a network. Now, sometime back, when we spoke about clustering in unsupervised learning, the clustering algorithm, it finds clusters of expected activity for each user and entity so that their observed values can be compared to these clusters. With peer group analysis, we go several steps deeper. And you can see that on this slide right here. Take a look at this. With peer group analysis, we analyze how an entity or a user behaves in comparison to other entities and users in a network over time. This will be used for cases where an event may be anomalous considering the past behavior of a specific user, but may not be anomalous considering the normal behavior of his or her peers. So initially, peer groups are identified and entities and users are put into different peer groups based on the behavior they have exhibited over time. A particular user or entity can belong to multiple peer groups as well. So let's take a very simple example. Here we saw that Steve was doing something that was anomalous, right? It was a time anomaly that was being exhibited by Steve. But let's imagine a situation where Steve is part of the marketing department, and there are maybe 12 different members in the marketing department. And it goes without saying that usually people in the marketing department all have to exhibit normal behavior that is very similar. So they may all exhibit behavior such as logging on at around the same time, logging off at around the same time, accessing similar kind of servers, similar kind of data. So basically, Steve would be put into the marketing department's peer group because of behavior exhibited. And even though a particular activity may fall out of what is expected for Steve individually, this particular activity may still be okay when you consider the larger peer group, and therefore this activity is not really risky. So that's what peer group analysis is actually going to help you with. And one of the algorithms that we can use to implement peer group analysis is called ConStream. So how does the ConStream algorithm really work? So we'll go a little bit into the technicalities right now in the ConStream algorithm, and we'll see how it works. So when data is received as a stream, it is possible that the data distribution may vary over time. That's very normal. So you can have clusters that are currently present in the data, but may be inactive at a future time. And there may be new clusters created as the data distribution changes. When the data distribution changes, it makes the already learned model obsolete, and something called a concept drift happens. Now, ConStream handles the concept drift in a very neat way. If any incoming data point doesn't fit into any of the existing clusters, a new cluster is created with this data point. Now, this new cluster could represent an outlier, or it could be a trendsetter. If no more points fall into the newly created cluster in the future, then it becomes an outlier. However, if other points begin to fall into this cluster, it becomes a trendsetter. When clusters remain inactive over an extended period, basically, you have a situation where no points are being added in that particular period, then the cluster is removed from the list of existing clusters, and this is called cluster death. Outliers can also undergo cluster death. Since the data distribution could be changed with time, recent points are given more weightage. The algorithm goes over each point only once, and thus it's fast enough to be used in a streaming setup. So that's how peer group analysis, one way of how peer group analysis actually can work. And then you have risk scores. Because at the end of the day, security analysts need something tangible to understand the measure of risk that a user or entity poses to the organization. And that is what risk scoring is all about. There are multiple ways to calculate risk scores, but one effective way could be to have a risk score for every user and entity that falls anywhere between 1 and 100. A risk score will enable an analyst to prioritize threats and decide what issue needs to be looked at first. To calculate risk, several actions need to be looked at closely for every user and entity. For example, there can be a separate risk score for each of insider threats, account compromise, data exfiltration, and logon anomalies. And then building upon these risk scores, we can also have an overall risk score for the user or entity. So now let's go over some examples of activities that should be considered when looking at insider threats. Account compromise, data exfiltration, and logon anomalies. Now, obviously, these activities that you see here, they are not an exhaustive list, and they are also not mutually exclusive. So you may have a few of these activities in insider threats that are also part of account compromise or data exfiltration or logon anomalies. but we'll just go over this so that you get a fair idea about it. For insider threats, an analyst can look at such things as data deletions across databases and files, abnormal file permission changes on hosts, unusual volume of user management activity, and abnormal EXEs run on hosts. For data exfiltration, we probably need to look at abnormal software installations, data hoarding activities, abnormal file downloads, and abnormal file creates in the network. For account compromise, we need to consider logon failure anomalies, multiple system file changes, and event logs being cleared unusually. And then finally, you've got logon anomalies. And here we may need to consider logon failure anomalies and logon success anomalies. And then for each of these possible anomalous activities, we'll need to give a weightage and a decay factor. A weightage is given to quantify the importance of a particular anomalous activity to the overall risk score. The higher the weightage, the higher the impact on the risk score. A decay factor is a metric that will reduce the dynamic risk score over time. The higher the decay factor, the higher the rate of reduction. For example, a decay factor of 0 will not reduce the risk score over time, and a decay factor of 100 will reduce the risk score to 0 very, very quickly. So we have looked at risk score for each anomalous activity, and then we have used that to calculate a user's or entity's overall risk score. Going on from there, building a timeline of anomalies is important to get the full context of a cyber attack. It will let us know and understand the sequence of steps that were followed before an attack actually took place. This information has to be available to the security analyst as they build evidence for an attack. Along with building evidence, they will also be able to see how each anomalous activity contributed to the overall risk score. So again, let's take an example here. We have that on the screen. So let's say that there is a particular user called Steve who has the highest risk score of 85 in the entire network. Now, on a dashboard, first of all, a security analyst needs to be able to see that. So they've got to be able to see that Steve is the riskiest user in the network. And this person has got a relatively high risk score of 85. And then once they deep dive into Steve's activities, they've got to be able to see a report of this sort. So here's all the list of anomalous activities performed by Steve. So what did he do? He first had multiple successful logon attempts. In fact, 102 such events were observed when the threshold is just 14. This was followed by 99 file permission changes when the threshold is only 3. He then went on to perform 80 system file changes and numerous file modifications as well. So 80 system file changes, that was quickly followed by 60 file modifications. And with file modifications, we see that what is expected, the threshold, is just 2 such events. Now, as a security analyst, if you look through this timeline and put together what really happened, you can also go one step deeper. For example, we just spoke about the multiple files that were modified by Steve. The security analyst needs to be able to click into this, and they should be able to see the objects, what the objects or the targets of the potential attacker were. So they've got to be able to see the list of files that were modified by Steve. Then bringing it all together through incident management. If you're using machine learning algorithms to just detect anomalies across users and entities, that may generate a lot of alarms. I mean, please don't misunderstand this. There is definite value in looking at users and entities and the risks that they pose. However, from a response point of view, it's imperative that security analysts classify multiple anomalies as incidents. Now, this can be done in 3 different ways. The first way is the manual addition. The analyst can manually add anomalies together as incidents. That's the easiest way to do things. It's going to rely on the analyst's intelligence to put together different anomalies and see them as part of that one larger incident. The second way to add anomalies to an incident is through the use of incident template rules. This again requires intervention from the analyst, but it automates the process to a certain extent. So with incident templates, the analyst creates a rule for an incident. They specify the criteria for incident creation, and all the anomalies that conform to that criteria will be automatically put into that incident. And then finally, the third way the machine learning way, the most innovative way, is to create incidents that would let the machine create incidents itself by using machine learning algorithms. So yes, you heard me right. Not only are anomalies being detected through machine learning, but here what we are saying is that incidents can be built using machine learning. Semi-supervised machine learning can be used very effectively over here. So the system can build incidents, and these can be shown to the security analyst, who then has to confirm that this really is an incident. And this can really take things to the next level. So we have discussed a lot of the theory so far with small examples. Let's take a look at a practical use case right now. We'll go over an example of a data exfiltration attempt. So that's what this example is that you'll see on your screen. Just take a look at this. So as you can see, there is an external attacker, and on day one, they send a legitimate looking phishing email with a malicious attachment to a front-end employee called Bob. The email contains a doc file that Bob clicks on, and without Bob's knowledge, malware starts being downloaded in the backend. So in this way, the attacker gets an initial foothold into the network and also compromises Bob's credentials. Then the attacker connects to the network from a remote location using Bob's credentials. This will trigger a pattern anomaly and increase the risk score associated with an account compromise. Then the attacker kind of lays low for a few days. As you can see, between days 2 and 7, there is no activity. And then the attacker is showing some activity on day 7 once again. So on day 7, the attacker gets a hold of a system administrator's credentials using a brute force attack. They have 10 failed logons followed by a successful logon on the 11th attempt, all within 30 minutes. Now, what is this going to do? This will trigger both a count anomaly and a time anomaly. And this will in turn raise that administrator's risk score associated with an account compromise. The risk score associated with the specific machine that was used to carry out this attack will also be raised. So at the same time, the user's risk score will be raised and the machine's risk score is also going to be raised. And then the attacker lays low for 2 more days and then shows activity on day 9 once again. So on day 9, the attacker uses the sysadmin's credentials to escalate Bob's privileges. Bob is made a member of a privileged security group. This is again going to increase the risk score of a possible account compromise. And then finally on day 10, the attacker accesses an unusually high number of databases with confidential data using Bob's credentials. This is again going to increase the risk score associated with data exfiltrations. So if the security analyst sets up an alert so that they get notified whenever the risk score of any entity or user goes over a certain threshold, such a data exfiltration attempt can be actually averted, because they get an alert in real time. As soon as a risk score is reached. So let's say that the analyst has created a rule so that whenever the risk score goes over 50, they get alerted by SMS or email. They can immediately take action right then and there. So that's how this is actually going to work for us. So this almost brings me to the end of my presentation, but I do have a few more things to show to you right now. And here are some of the next steps that we can do together. So one of the things that you could do if you want to learn more about user and entity behavior analytics and how you can use machine learning in cybersecurity is go to our UEBA page. Let me quickly navigate over to the page right now. So here is our UEBA page, and let me copy paste this so that you can access this at your convenience. I'll just be posting this on chat. And then from here, if you were to navigate over to UEBA resources, you've got a lot of resources here. And there's a particular resource that I want to point you towards. That's the white paper. It's going to basically explain to you what UEBA is from the ground principles. I know I'll recommend that all of you take a look at this white paper whenever conveniences permit. So I'll just post that URL on the chat as well. And then apart from that, on the same page, you can also take a look at the interactive case studies. And we'll be going over, in this particular case, interactive case studies, there are 3 different situations that you can go over. So there's a case of an insider threat, account compromise, and data exfiltration. So you can take a look at 3 case studies over here as well. So if you'd like to access all of that, you can just go onto that UEBA page and access all of that. And I have one more thing that I want to show to you, which I think you'll find really, really interesting. That is this. This is our Log360 UEBA demo page. So a lot of the things that we covered today is available in Log360 UEBA, and this is free for anyone to try. So you can just go onto this demo page and take a look at this whenever conveniences permit. You can just play around with this particular solution. For example, you can navigate over to anomaly reports, and you'll be able to see different kinds of anomaly reports based on time, count, and pattern. Some of the things that we went over today. Let's take a look at all of this. So here, these were some of the concepts that we went over today. So let me paste this URL on the chat as well, so that you can access this whenever you can. Of course, you can always ask for a personalized demo. That is always there. So if you want us to show you a demo of how Log360 UEBA works, please let us know. We're always happy to do that. So great. Before I let you go for the day, I do have a couple of polls that I have to run right now. So if you can take a moment and answer a few questions for me, which I'll be launching as polls, that would be really great. So I've just launched a poll right now, which you should be able to see on your screen. Question number 1 is, which of our other solutions are you currently evaluating, if you're evaluating, that is? And question number 2, do you want our product specialist to assist you with a free evaluation of the solution? Obviously, in a 40-minute webinar like this one, there is only so much that I can cover. And I'm pretty sure I wouldn't have covered all the use cases that you're interested in. But if you'd like us to go over Log360 UEBA for your specific organization's environment, we'd be very happy to do that. Please let us know. All right, I see a lot of responses coming through. So I'll just give this another 10, maybe 15 seconds. Thank you so much for these responses. It's going to really help us out. All right, let me go ahead and end this particular poll, and I have one more poll to run right now, and that is going to be about the session feedback. So if you can take a few moments and let us know how this webinar experience was for you today, that would be really great. So you have that poll on your screen right now. And just as you're answering that, let me remind you that part 2 of this webinar series happens at the same time next week. And next week, we'll be taking a more futuristic approach. We'll be looking at what we have in store in the years to come when it comes to machine learning in cybersecurity. We'll be going much more beyond machine learning. We'll be talking about artificial intelligence and deep learning and how those can be used for cybersecurity as well. And we'll be also taking a closer look at Log360 and what the solution can do for us in a practical sense. So all of that is going to happen, next week. So same time next week, I hope you can all join us once again. All right. So thank you all so very much for being a part of this webinar today.